Welcome to Lesson 2.2 of the Grade 11 Physics series. Today, we will be taking a deeper look into moving objects, focusing on the concepts of speed, velocity, and acceleration. In this lesson, we are covering how speed and velocity are the same yet also different, as well as what acceleration really is. Then, we will define the terms uniform motion and accelerated motion in order for you to understand them effectively. In the previous lesson, we defined distance as either the space between an object and a point, or the total length of the path traveled by an object. And so, therefore, the speed of any travel can be calculated by taking the total distance traveled divided by the time taken to complete this travel. Speed is a scalar because you are dividing one scalar, distance, by another, which is time. And we divide by delta t because really what you are working with in the denominator is the rate of change in time. And one more thing to mention, we call this average speed because, well, in some situations, speed does not stay constant. The distance covered per unit of time may vary, meaning that the object may travel at different speeds during different parts of the trip. Now take a look at this red car in the bottom. We see that it has traveled a distance of 20 meters in 4 seconds, and so we can solve for speed with these numbers right here. So v is equal to 20 meters divided by 4 seconds. And so the speed of this red car is 5 meters per second. We also defined displacement as the change in position of an object. Now, velocity can be calculated by taking the displacement of an object and then dividing it by the time taken for this displacement to occur. Now, since displacement is a vector and time is a scalar, then velocity is also a vector. Another thing to mention is that since displacement is the difference between a final and initial position, then we can write velocity as equal to df minus di, or the vectors df and di to model position, divided by delta t. And we call this average velocity because in some situations velocity does not stay constant, and an object may move at different velocities during different parts of its motion, which can even happen if its direction changes. And so we have some numbers down here in the bottom corner where the vehicle is moving 20 meters west in a matter of 4 seconds. And so we can solve for its velocity. So the velocity of the red car is 20 meters west divided by 4 seconds. And then you get a velocity of 5 meters per second west. Now, let's work on a problem. You walk 10 meters east to pick up your car keys and then walk 25 meters west to leave your front door. If this entire travel took you 30 seconds, what was your average speed? What about average velocity? So the first thing that we need to do is calculate what was the total distance traveled. Since we don't care about direction in this, we can just add 10 meters to 25 meters. Then we can divide this by 30 seconds. And if you run this through your calculator, you should get an answer of 1.16 recurring meters per second. And then rounding this to significant digits, you can just say that the average speed is 1.2 meters per second. Okay, that's great. But what about average velocity now? So here we're going to be working with two displacement vectors. And so I'm going to say that the average velocity is equal to 10 meters east plus 25 meters west divided by 30 seconds. To calculate the total displacement, we're going to be working with vector addition, or you could say vector subtraction in this case. Since the 10 meters is the smaller quantity, I'm going to say that this is negative 10 meters west plus 25 meters west. Let me just fix that. Divided by 30 seconds. And so calculating minus 10 meters plus 25 meters, you should get a result of 15 meters west divided by 30 seconds. And then your answer should be 0.50 meters per second west. And we're going to add that extra 0 here to adhere to the 2 significant digits that are required. If your velocity is changing over some length of time, then you are working with acceleration. Average acceleration is the change in velocity divided by time, and some examples where it is present include walking east and then walking west, slamming on the brakes when a car is in motion, or even something as simple as an apple falling to the ground. Acceleration is a vector because we're dealing with velocity, which is also a vector, and because you're dividing that by a scalar, which doesn't really have an impact on if it's a scalar or a vector, then acceleration is indeed a vector. And since really, well, this is actually the rate of change in velocity, and so acceleration can be rewritten as equal to the final velocity minus the initial velocity of whatever object you're dealing with divided by time. Let's work on this question now. A car is moving at a velocity of 5 meters per second east before it speeds up to a velocity of 20 meters per second east. This takes a total of 3 seconds. With this information, what was its acceleration during this time? The first thing we're going to do is write our equation, which is that acceleration is equal to the final velocity of the car minus its initial velocity divided by the time taken. And so we can fill in these variables where the final velocity is 20 meters per second east minus the initial velocity of 5 meters per second east. And then we're going to divide this by 3 seconds. In the numerator, you should get 15 meters per second east divided by 3 seconds. And then you should get an acceleration of 5 meters per second squared east. Two key terms to understand are uniform motion and accelerated motion. Uniform motion is present when an object moves at a constant velocity without speeding up or slowing down. To help you visualize a little bit of what this means, and as a little teaser for the next lesson, imagine taking a picture of a moving car exactly every second. If the car is moving at a constant velocity, the car would cover the same amount of distance in every second, right? So in a motion diagram like what we have here, the dots would be evenly spaced apart. And to be clear, each of these dots represents the position of the car at equal time intervals. Since the spacing between the dots is the same, then this proves to us that the car is indeed moving at a constant velocity. Then in regards to accelerated motion here, you get that when an object's velocity changes over time, speeding up or slowing down. And in a motion diagram, accelerated motion is evident when the dots here are not evenly spaced. As the dots here are getting further apart, well then, we know that the car is indeed speeding up. In summary, we analyzed speed, velocity, acceleration, and the terms uniform and accelerated motion. In the next lesson, we are going to explore graphs in the world of kinematics, such as position time, velocity time, and acceleration time graphs, all of which help to describe an object's movement through some space. We will of course learn how to draw such graphs from given data and how to interpret them effectively. As always, thanks for watching, and like this video if you found it helpful. Subscribe to follow along with the rest of the series.